notes for 7.2, Properties of Rational Exponents. This section is actually split into 2 days, so this is day 1, and then the next video will be for day 2. If you recall, in the first part of chapter 6, we looked at properties of exponents with integers. So today we're going to look at properties with rational exponents or fraction exponents. Our exponent rules still apply. They're the same. We're just going to look at them with fractions. So if you recall, our multiplication property, we keep the base the same and add the exponents. So for example, if we have x cubed times x to the 4th, we add the exponents, this gives us x to the 7th. The second rule is the division property, and that is if we keep the base the same and we subtract the exponents. So if we have x to the 5th over x squared, remember we subtract our exponents, so 5 minus 2 is 3, so this simplifies to x cubed. And lastly is power to a power property. Again, we keep the base the same and multiply the exponents. So for example, if we have x cubed and we're squaring that, 3 times 2 is 6, so this is x to the 6th power. So again, these rules still apply even when we have fractions. So for example A, we have 6 to the 1/2 times 6 to the 1/3. Now we know if we have common bases and we're multiplying, we have to add the exponent. So we have 1/2 plus 1/3. We know that we have to have common denominators in order to add. So we know that our common denominator is going to be 6. So I have 6, 1/2 is the same as 3/6. So this is 6 to the 3/6. 1/3 is the same as 2/6. So 6 to the 2/6. And then again, we're adding these. So 3 plus 2 is 5. So this is 6 to the 5/6 power. So again, if we have common bases, we still add the exponents. Example B, we have 27 to the 1/3 times 6 to the 1/4, and all of that is squared. Notice we have power to a power, so we can distribute the square into everything inside of the parentheses. So this is 27. 2 times 1/3 is 2/3. So 27 to the 2/3 power. Times 6 to the 2 over 4 is 1/2. So this is 6 to the 1/2 power. Now notice we do not have common bases, so we can't combine these things. We can't add them, but we can simplify 27 to the 2/3 power based on what we learned in the last section. So remember, we can rewrite this as the cubed root of 27, and all of that is squared, and then we still have our 6 to 1/2. Now the cubed root of 27 is 3, so this is 3 squared, and again we still have 6 to the 1/2. 3 squared is 9, so 9 times 6 to the 1/2. You could leave it like this, or we know that the 1/2 power is the square root, so we can write it as 9 to the square root of 6. So that is your final simplified answer. For example C, we have 4 to the 3rd power times 2 to the 3rd, and all of that is raised to the negative 1/3 power. So again, we're going to distribute, because this is power to a power. So 4 to the 3rd, we multiply 3 times the negative 1/3, that gives us negative 1. So 4 to the negative 1 power. And 2 to the 3rd, all raised to the negative 1/3 power, is 2 to the negative 1. If you recall from chapter 6, our exponent rules, if we have negative exponents, remember that's like taking the reciprocal or flipping. So 4 to the negative 1 is the same as 1/4, and 2 to the negative 1 is the same as 1/2. And then we can multiply these. 1/4 times 1/2 is just 1/8. For example D, notice we have division or a quotient rule. 6, if we have nothing written, is to the 1st power. So remember, we subtract our exponents. So we're going to have 1 minus 3/4. So 1, again, we want a common denominator of fourths. So 1 is the same as 4/4 minus 3/4 is 1/4. So that gives us 6 to the 1/4 power. Or we could write this as the 4th root of 6. Either way is correct, unless it tells you to write it in one way or the other. Either way is correct. In our last example on the first page, we have 18 to the 1/4 and 9 to the 1/4, and all of that is cubed. Notice here that we have a common 1/4 power inside our parentheses. So what we can do is the opposite of our power to a power. So we can take 18 over 9, and we can raise all of that to the 1/4 power. And again, all of that is cubed. Now, if you notice our fraction here, 18 over 9, 18 divided by 9 is just 2. So this is 2 to the 1/4 power. And again, all of that is cubed. Now we can distribute our 3. So we're going to multiply 1/4 times 3. So this is 2 to the 3/4 power. And again, that is our final answer. So again, we can use the exponent rules that we have learned in Chapter 6, and we can apply those to rational exponents as well. Example 2 says to write the expression in simplest form. So again, the rules that we learned about radicals in Chapter 5 when we were simplifying radicals apply when we have radicals other than square roots. So we're going to simplify the same way. We're just looking for different groups. If you remember, when we were looking at square roots, we were looking for groups of 2 to factor out of the radical. Now we're looking for whatever our index is, that's the number of groups that we are factoring out. So for part A, we have the 4th root of 64. We're going to simplify this just like we did before using our birthday cake method. So again, we're looking for prime numbers that are divisible by 64. So if we start with 2, that will give us 32. Again, we can divide by 2 again. That will give us 16. Divide by 2 again will give us 8. Divide by 2 again will give us 4. Divide by 2 again will give us 2. And divide by 2 will get us 1. So now, notice our index here is 4. So we're looking for groups of 4. Again, when we were looking at square roots, we were looking at groups of 2 because our index was 2. So whatever your index is, that's the number of groups that we're looking for. So here we have 4 2's. So we can bring a 2 outside of our radical times the 4th root of whatever we have left over. So our leftovers are 2 times 2. We're going to multiply those together, and then we get a 4 underneath the radical. So our final answer is 2 times the 4th root of 4. Example B, we have the cubed root of 25 times the cubed root of 5. If you recall, again, with radicals, if we have a common index, we can multiply what's underneath the root. So here we have the cubed root of, we can multiply 25 times 5, which is 125. So then again, we can do the birthday cake method. 125 divided by 5 is 25. 25 divided by 5 is 5. And again, we end up with our 1. So again, our index is 3, so we're looking for groups of 3. Notice we have 3, so our answer is just 5. So the cubed root of 125 is just 5. For part C, we have the cubed root of 32 over the cubed root of 4. Again, we're going to use the same rules that we talked about in the last section. Now notice 32 and 4. We can divide both of those or simplify. So if we have the cubed root of both the numerator and the denominator, again, we can pull that out and take the cubed root of 32 over 4. Now 32 divided by 4 is just 8. So this is just the cubed root of 8. And then again, we know that the cubed root of 8 is just 2. In part D, we have the 4th root of 7/8. Now notice we can't simplify 7/8. So that's when we want to take the square root of, or the 4th root of both the numerator and the denominator. Now, we cannot have radicals in the denominator just like we couldn't have square roots in the denominator. So we can't have any kind of radical in the denominator. So we have to multiply both the numerator and the denominator by a number that will get rid of the radical in the denominator. Now, if you remember, when we had square roots, we just multiplied by what was ever in the denominator. But I want you to look at this with me. If we think about 8, if we factor do our prime factorization or birthday cake with it. We can divide that by 2. 4 we can divide by 2. And we have a third 2. Now, we have a group 3 2s. Now, our index is 4, and we want a group of 4. So we're going to multiply this by the 4th root of 2, because again, that will give us that 4th 2. So whatever we multiply the numerator by, we also have to multiply the denominator by. So if we multiply this out, oh, there should be 2 up there as well. So we have 7 times 2, which is 14. So we have the 4th root of 17, all over 8 times 2 is 16. The 4th root of 16 is just 2. So that got rid of our radical in the denominator. So again, in order to get rid of the radical in the denominator, we have to multiply by whatever number is going to give us a full group based on the index. And our last example is adding and subtracting roots and radicals. So we're going to perform the indicated operation. Now, if you recall from algebra in general, in order to add things together, they have to be like terms. The same is true with roots and radicals. In order to combine roots and radicals together, they have to be like terms, or they have to be the same. So in order to combine like terms, we must have the same exponent or the same radical. Again, we cannot combine like terms or cannot combine things together by adding and subtracting if they aren't alike. So for part A, we have 5 times the quantity 4 to the 3/4 power plus 3 times 4 to the 3/4 power. Now if you notice, we have 4 to the 3/4 power in both of these. Since they are the same, this is the same as saying that they are like terms. So again, it's like having an x. It's like saying 5x plus 3x. They both have an x, so we can add them together. So we're just going to add the coefficients. So 5 plus 3 is 8, and we're going to leave the exponent alone. So 4 to the 3/4. So this is 8 times 4 to the 3/4, and that's as simplified as we can get it. Now for part B, we have a cubed root. So again, we're looking for like terms. So if we look at the cubed root of 81, we can simplify this. Again, we're going to do your birthday cake. So 81 we can divide out a 3. That will give us 27. Divide out another 3. That will give us 9. Divide another 3. That will give us 3. And 3 is our last one. Again, we're looking for groups of 3 because 3 is our index. So we have 3 3s. So that's going to go outside of our radical. And again, whatever's left over, we multiply together and put underneath the radical. So we have 1 3 left over. So this is the same as 3 times the cubed root of 3. Now notice, in our second term, we just have the cubed root of 3. So we can combine these together. Now again, if there's no number out front, remember that's the same as saying a 1. So 3 minus 1 is 2. And again, the cubed root of 3 stays the same. So again, we have to have the same radical or the same exponent in order to combine. So we may need to simplify things first to get them the same, but then we can combine them once they have the same exponent or radical. So again, the rules that we learned before about radicals and exponents still apply when we have rational numbers and different indexes for our radicals.